Scholar blocks harder than any other Google property. The user base is smaller. Scraper patterns stand out more clearly. And the rate limits trigger faster than search, maps, or anything else Google runs. But the data is gold. 669,000 results for one query. Real academic papers from Cambridge, MDPI, Elsevier, Springer, citation counts, author profiles. We just need to get past the front door. Open the Scrape.do dashboard. Grab the API token. Build the search URL. Scholar uses a clean URL pattern. The Q parameter for the query, URL, encoded with quote plus. The HL parameter forces English. The AS_SDT parameter sets the search type to articles. Wrap every request through Scrape.do with super equals true. No render needed, Scholar is server-side rendered, the HTML comes back with everything in it. Super handles the IP rotation and the TLS fingerprinting. That's the entire bypass. Now, the pagination loop, Scholar serves 10 results per page. Page 1 has no parameter. Page 2 is start equals 10. Page 3 is start equals 20. Multiply the page number by 10, build the URL, fetch through Scrape.do, 1 second delay between pages. This is not optional. Skip it and Scholar will block your IP faster than any other Google service. Open DevTools on the search results page. Hover over the first result. The tooltip shows div.gsr.gs or .gsscl. That's the outer container. Drill into the DOM. Every result wraps inside a div.gsri container. Inside that, 4 anchors that survived years of Google front-end rewrites. h3.gs_rt for the title heading. Inside it, an A tag with the actual paper link, div.gsa for the author line, names, journal, year, publisher, div.gsrs for the snippet. The search results excerpt with the bolded keyword highlights. 4 selectors. That's all we need. Back to the editor. Loop over every div.gsri container. Pull the h3 title. If it wraps an A tag, grab the link. If not, citations and books sometimes ship without links. Fall back to the heading text. Pull the snippet from GSRS. Pull the author line from GSA. Append a clean dictionary to the results list. Run it across 3 pages. 30 papers extracted. Open Scholar search results JSON. First entry. Is breakfast the most important meal of the day? From Cambridge. Second. The effect of breakfast prior to morning exercise? From MDPI. Third. Breakfast and behavior in morning tasks? From Elsevier. Real publisher links. Search done. Now, content. The next pipeline is paper downloads. We have 30 URLs, but they point to 30 different publisher domains. Cambridge has one anti-bot stack. Elsevier has another. Archive has none. PubMed Central is wide open. Springer is locked down. One strategy won't fit all of them, so we build a fallback chain. 3 tiers. Tier 1, basic, no flags, cheapest and fastest. Works for Archive and PubMed Central, where the HTML is open and there's no protection. Tier 2, super equals true. Engages Scrape.do's full anti-bot bypass. Handles Cloudflare, publisher paywalls, most journal sites. Tier 3, super plus render. Full headless browser execution. Last resort for JavaScript-heavy journal pages that load content after initial render. Escalate cost only when necessary. A successful response means status 200 and body longer than 100 characters. Short responses usually mean a block page or empty content. Now the download loop. For each paper URL, iterate through the 3 strategies in order. On success, save, and move on. The magic flag is output equals markdown. Scrape.do strips navigation, ads, headers, footers, everything that isn't the actual paper. What comes back is clean markdown text of the abstract or the full content. Zero parsing code on our end. Sanitize the title into a file name. Prefix with a 0 padded index. Save to disk. Run it. Paper 1. Basic failed, super okay. Paper 2. Basic okay. Paper 3. Basic failed, super plus render. Okay. The chain works exactly as designed. 27 research papers downloaded. Clean markdown files in the Scholar Articles folder, ready for analysis, embedding, or LLM training. Now the third pipeline, author profiles. Open the James Betts profile. Verified email at bath.ac.uk. 6,199 total citations. H-index 43. I-10 index 97. Hundreds of papers, going back to 2007. One profile, 6,000 citations. We're going to grab all of it. 3 selectors for the header. Div hashtag GSCPRFIN for the name. Div.GSCPRFIL for the affiliation. Div hashtag GSCPRFIVH for the verified email notice. 3 find calls, 3 text extractions. For the citation metrics, target the table with ID GSCRSBST. 3 rows, citations, H-index, I-10 index. 2 columns each, all time and since 2020. Walk the rows, match the citations row, pull both cells. Now, the article list. Scholar shows 20 articles by default. There's a Show More button at the bottom that triggers an AJAX call for more. We don't click it. We skip the button entirely. Instead, manipulate the URL directly. Add susstart for the starting index and page size capped at 100. Loop until a page returns fewer than 100 rows. That's the end of the list. No headless browser, no JavaScript execution, no click events. Pure URL parameters. Each article row sits inside tr.gscatr. Title in a.gscapp. Authors and journal in 2 consecutive div.gs gray elements. Citation count in a.gscaac. Year and span.gscah. 5 fields per row, all plain text. Run the author scraper. Page 0 to 100. Page 100 to 200. Page 200 to 287. The pagination ends naturally when the page returns fewer than 100 rows. 287 articles saved to Scholar Author Articles JSON. Open the file. The causal role of breakfast in energy balance and health, 318 citations, 2014. Liver glycogen metabolism, 290 citations, 2016. The causal role of breakfast in obese adults, 240 citations, 2016. Exercise-induced browning of adipose tissues, 233 citations, 2018. A complete publication record. Every paper, every citation count, every co-author, every journal. The kind of dataset academic search engines spend years building. 3 pipelines, 1 bypass. Search results, markdown papers, author profiles, every one of them through the same flag. Full code on GitHub. Free credits at scrape.do